Good afternoon everybody, and welcome to the Voltimum webinar series. We've been holding on for a couple of moments to allow some extra time for people to join into the webinar. I think it's time that we could make a start because we realise that your time is quite valuable. My name is Richardson from ABB, and I'll be presenting the first part of this presentation. Following after myself will be Martin Muxworthy from Nexans Olex cables. Just a little bit of housekeeping. If you have any questions that you would like to ask during the presentation, you can use the Q&A chat box, which you could see on your screen. I think you'll find it on the lower left-hand side of your screen. Martin and I will try to answer any question that pops up on that chat box as they come up. If there's a particular question that's going to require quite a long answer, we may say to you that we'll hold that question until the end, just so that we're not holding up the presentation too much for other people. But in general terms, we'll certainly be trying to answer each question as it comes up. At the end of the Voltimum webinar, we'll also be asking everybody to participate in a quick little survey, and we would really appreciate if you wouldn't mind sticking around and offering your feedback for that. It'll only take about 20 seconds. So as I said, my name is Ian Richardson from ABB. What we're talking about here is tackling energy efficiency, which we have spoken about on a number of the other webinars that we've had in this series. Some of the reasons that we might want to consider energy efficiency, particularly in relation to buildings, could be the specification requirements that could be relating to a particular project. There are Green Star ratings. Those that may not be familiar with Green Star, it's a national voluntary environmental rating system, and it evaluates the environmental design on the construction of buildings. The Green Building Council of Australia manages this particular scheme. There's also a thing called the Neighbours rating. That is actually run by the New South Wales Office of Environment and Heritage. Although that's a state-based organisation, they maintain the Neighbours scheme on behalf of the Commonwealth and the various state and territory governments. This is a scheme which has seen as a bit of a national rating scheme that measures environmental performance of various buildings, and it gives you a comparative energy performance scale that owners and tenants can view and compare their energy efficiency. The last reason that you might consider energy efficiency, and probably the most important one, is of course we're going to try and save some money. Sometimes a bit of an investment on a particular system or a particular infrastructure will give long-term benefits in trying to save some money against the cost of energy, which is obviously a very big consideration these days. There's been a number of studies have been carried out in various parts of the world, and they've come up with pretty much the same response. Consistently, it's saying that buildings consume about 41% of the energy consumption of the world. So as you can see, there's a significant focus is going to come into building efficiency to try and save energy. In the other webinars, we've discussed various building automation type of methods to try and increase our building energy efficiency. Some of these could involve various forms of lighting control. It could be brightness control, daylight harvesting techniques. We can operate sun shading through the automation of blinds and shutters to keep the sun away from windows, or we could deflect shutter angles so that direct sunlight's not coming in and light is, so we can get the greatest benefit of a daylight harvesting type of system. Heating, ventilation and cooling controls, if we can maintain that better in conjunction with the other forms of automation, that will provide us with some opportunities to save energy. And of course energy monitoring. Once we are putting in various facets of our automation system, we need to actually measure what the result is so that we know that we are actually saving money and doing what we're proposing to do. A lot of these techniques that's been proven can provide direct energy savings, and it can be anywhere from 15 through to about 50% or more, depending on which systems you've employed or what combinations of systems you might have done. Looking a little bit deeper, I've spoken on a few occasions about the KNX system. KNX is certainly one of the automation systems that's utilised in various parts of the world. Fortunately, it is the only one that actually is backed up by an IEC standard. But in this system, it encompasses a variety of different areas of the building controls, as you can see on the list. So anything from lighting and heating and blinds, as we've already spoken about, but there's a variety of other things that can be incorporated into this system as well. The concept of the KNX system as a viable automation system, it has a lot of advantages, because KNX is, in fact, it's nothing to do with a particular manufacturer or a vendor. So there's about 360 different manufacturers, and it's kind of a who's who of various people in the industry. And by operating in this particular realm with KNX products, all of these manufacturers will operate on the same system, and the interoperation is effectively guaranteed. So it's a great feature of the system. This then allows a very competitive environment, because you're not dealing with one brand, and I'm sure a number of you are electrical contractors and you are going to be very, very price conscious. Using a system like KNX, because you're not tied to a particular manufacturer, means you've got the choice. You can choose a product at the price point you're looking for. You can choose the particular features of one manufacturer that might be different to another one, and that's all going to suit the particular application you've got. And as we can see here, there's quite a number of different applications can all live on this particular KNX system. That's a brief introduction on automation, just to gloss over it. If there are no questions, which none have popped up just yet, I will pass you over to Martin, because Martin's got a really interesting topic talking about energy efficiency and the ways that we can save some money, and it's through the use of clever cabling, which is, as you would have seen from the title. So Martin, I'll pass the baton over to you, and you can take charge from here.
Good afternoon, everyone. As Ian introduced, I'm from Nexans Olex Cables in Melbourne, and welcome everyone this afternoon. Yeah, the topic that I'm going to talk about, the principles are not new, but maybe applying these principles to the cables sizing is what could be deemed to be a little bit novel. I wrote about this topic and was wrote a paper which was published on the Voltimum website earlier this year, so some people may have got a bit of an insight as to what I'm going to talk about, and really this is this topic is gaining momentum, even to the extent that it is going to be introduced at Standards Australia level. So that's one of the reasons for continuing to discuss this topic. The first slide talks about established cable sizing methods, and this is where we start with this topic. There are 4 basic parameters that need to be taken into consideration when selecting a cable size. The cable selection process must satisfy all 4 parameters, and each parameter by itself can be the determining factor or the limiting factor in terms of picking the final cable size. We'll briefly look at each parameter because I think it's important to understand first where these, how to apply these. The continuous current rating of a cable, and I often refer to that as just the cable current rating. If we break down what that actually means, it simply means that the cable must be sized adequately to ensure that the cable does not overheat when a current is passed through it. Heat is generated whenever current passes through a conductor which has an electrical resistance, so therefore bigger conductors can carry more current because their resistance is lower. Added to this is the ability of the cable environment to dissipate the heat generated by the conductor, so the cable materials and the environment in which the cables are installed in, such as underground ducts for example, or the soil itself, will all have an impact on determining the cable rating. So cables installed in a better thermal environment will have a better cable rating. The next parameter is voltage drop, which in essence must be limited to ensure that electrical devices operate properly, and the current rule in Australia states a limit of 5% on voltage drop. Voltage drop is primarily related to the resistance of the conductor, which is length dependent, and therefore circuit distance also strongly contributes to voltage drop. These two are, you'd probably say, are the most often used parameters that will be used to determine the appropriate cable size for an electrical installation. And a couple of general rules of thumb are that for circuits less than say 100 metres, the current rating is more likely to determine the cable size, and for circuits more than 100 metres, voltage drop is more likely to determine the cable size. Of course there's going to be some exceptions. This is just a general rule that people can adopt. Earth fault loop impedance was introduced in the wiring rules not too long ago, is the next parameter, and this was introduced because it's important to ensure that the impedance of the cable, which is the conductor and the earth return, is low enough such that the cable protective device, for example circuit breaker or fuse, will operate in the event of an earth fault. Therefore both resistance of the main conductor and the earth conductor is important, and because these are both length dependent, then obviously circuit length is also critical. Next is short circuit rating, which does not often determine the appropriate cable size, as a cable meeting the first two parameters will generally also meet the requirements of short circuit rating. Needless to say, it needs to be kept in mind so that a cable is able to withstand a prospective short circuit current that could flow in the unlikely event of a short between, say, a phase conductor and an earth conductor. In the last parameter, distance is not an issue. All of these four parameters are based on safety, and the intent is to protect persons, livestock and property from the risk of electric shock, fire and physical injury hazards. Each of the following dot points briefly shows how these cable sizing principles relate to these safety considerations. And it might seem fairly obvious, the current rating, for example, you need to limit the current that flows in the cable to stop it overheating, which could lead to premature failure and the possibility of fire. So you'll find in most of those fire and the risk of shock are related to each one of those parameters. These cable sizing principles are not just based on good engineering practice. They are defined in the relevant Australian standards, and they are mandated by law. AS 3000, which electrical contractors would know very well, is called up by law in each state's electrical installation rules, and this document is a document that describes how electrical equipment should be installed to ensure that persons, livestock and property are protected from the risk of, like I said before, electric shock, fire or physical injury hazards. AS 3008.1.1 is another very important standard which is referenced in AS 3000. It's the cable selection guide. It provides expanded tables of current ratings broader than that contained in AS 3000, and also includes current ratings, AC resistance values and voltage drop factors, and much more data needed to perform cable sizing calculations. It is important to note that the cable sizing methods discussed so far result in the smallest cable size, which in turn gives the lowest installation cost, and there is no consideration with any of these methods given to operating costs, for example, which are the cost of losses which are incurred by the owner of the installation. Whenever any cable carries a current, a loss results and there's a cost associated with that loss. No, is the audio still coming through okay, Ian?
Be working fine. I hope everyone can hear us well.
Okay, I just had a message come up about had we stopped, and maybe it was just the pause between slides, perhaps. So when considering energy efficient cabling and the cost of losses, we see that the total lifetime cost of electrical installation comprises the initial cable installation cost, which is what we've been discussing so far, plus the additional cost of operating the installation, i.e. the cost of electrical losses. Broadly speaking, energy efficient cable selection gives the lowest lifetime cost and the optimum in terms of energy efficiency. I might be a bit bold in saying that electrical contractors, installation contractors, are largely interested in the installation cost, while owners of electrical installations are interested in the total lifetime cost. Installation designers, such as consulting engineers, large installation contractors that have the owner's interest in their considerations, are interested in both installation cost and total lifetime cost. And ultimately, a compromise will need to be struck between the most energy efficient design and the lowest installation cost. Moving on, tackling energy efficiency with clever cabling. So how do we start when considering energy efficient cable selection? I just thought I'd add this one in here as a quick refresher about how energy efficiency can be applied, and it is only applied when the cable size is selected based on current rating, because the current rating is dependent on thermal consideration, where cable losses is a key requirement. The equation I've shown there, don't worry too much about it. It's well established and documented in IEC standard 60287. I'm not going to go through it here, but it's just used as an example that it's an established equation that tells us how to calculate the current rating of a cable, and to note that this equation is used in AS 3008 to calculate all of the ratings that are in there. So I think the important part is we move on to showing how we tackle energy efficiency with some clever cabling solutions. The best way to do this is to consider an example. I've picked a simple example just to demonstrate what we're talking about here. Let's take a 400 volt three-phase system where we need to deliver, say, 250 amps over 75 meters. The cable that we're going to choose is a single core copper XLPE insulated PVC cable, let's say installed in trefoil configuration, laid on cable ladder tray, unenclosed in free air and protected from direct sunlight. The initial solution is obtained by referring to AS 3008, Table 8, Column 9, and you'll find a 95 square mil copper cable has the required rating of that exceeds 250 amps, and that's 298. The first thing we do is check the voltage drop, make sure we're within that 5% limit. Again, referring to 3008, we get the appropriate voltage drop factor from table 40 and calculate the voltage drop for that circuit. And we end up getting 8.6 volts or 2.1%. So just need to check that first and to make sure we're ready to move on to considering energy efficiency with this particular circuit. Step 1, calculate the losses and the costs of losses for that initial solution. Since losses are a direct result of the ohmic losses in a conductor when a current flows in it, we use the AC resistance value that's given in AS NZS3008, and the following formula shows how it's applied to get the losses in watts. Note that the units of resistance and the circuit length must be the same. In other words, if the resistance is in ohms per kilometres, which is what's given in AS 3008, then the circuit length must also be used in terms of kilometres. That's why I've got 0.075 in the equation. So they're quite simple equations to use, and use of spreadsheets will make this quite simple. Next, we consider the cost of losses. Typical energy costs today, I haven't got an updated value, but I've used say 15 cents per kilowatt hour, remembering that the definition of a kilowatt hour is a load of 1 kilowatt running for 1 hour. So therefore we had 3,473 watts that we calculated in this example. That results in a figure of 3.47 kilowatt hours. One thing we need to also be mindful of is that of the utilisation of the circuit. Cable circuits seldom operate at full load continuously, so whenever you're calculating losses you need to factor in a utilisation figure. In practice loads fluctuate, so we need to give an estimate or make an assumption about the utilisation factor that we're going to apply in this exercise, because it does make a large difference on the overall loss calculation and the cost of losses. I used a value of 80%, something typical for, say, a supply mains circuit. So what we end up doing is adding in the calculating the cost of those losses over a 1 year period using that previous loss value that was calculated, and we get a total loss for the year of $2,921. The next step is to calculate the total cost of the installation, which includes the cost of the losses and the cost of the cable. And again, I've used some nominal list pricing that you can get from most cable manufacturers, and then you can work out the total cost of the cable. So we've got 75 metres, we have 3 phases. I've used $12 per metre, and then add that to, say, a 20-year estimated life asset. We have to add 20 years by the 2,921, end up with a total cost of 61,120. I guess the first observation that we can make here is that for that example, the cost of losses comprises a very significant component of the total cost of the installation. So immediately we can see that this example lends itself greatly to an energy efficient cable sizing method. So next step, what we do is we start tabulating some numbers, and again a spreadsheet is the best way to do this. We progressively use or repeat the same calculation for every size up from that initial solution, and we calculate out the losses and the total installation cost for each size. So we go up from 95, we go to 120, 150, 185 and so on. And what I've done is highlighted in red the total cable cost, or I should say the highlighted value is the one with the minimum total cable cost. I'll say that again. The red is the value representing the total asset cost, so the total cost of losses and the cable cost, which is the lowest. Some more observations that can be made. The total cost drops rapidly when choosing a conductor size, say only one or two sizes above that minimum size. As you can see on the right hand column, we go from 61,000 to 49, 41, so it drops rapidly as you go up one or two cable sizes. So, and the optimum size in this example tends to be many times larger than the minimum size, but you'll notice that it does approach what we call the law of diminishing returns. So as the conductor size increases, the gains become smaller and smaller. One thing that needs to be highlighted is that although the 500 square mil seems to be the best option, there are some assumptions that aren't taken into account and which we will explore next. I've already covered a couple of those observations in the previous slide, and as I was alluding to, the optimum size of 500 may not be practically the best option. Some of the things that we haven't taken into account is that when you go up in conductor size, you'll need extra space to install the larger cable. Difficult to account for this in this example or this calculation. There's extra effort and cost associated with installing a larger cable. I'm not just talking about the cost of the cable itself here, I'm talking about the extra effort, you know, the extra weight on cable trays and so on, the extra manpower, and it will no doubt take longer to install the bigger cable. Again, that component is difficult to allow for in this example. One of the more obscure things that we can account for is that, well, because you're not paying for the cost of losses, it is possible to actually invest that money that can be earned, and there's a windfall, if you like, by not having to pay for those losses. But to account for that, we need to use a financial function, and that's called the net present value, or NPV. So this is what next needs to be added to our table to determine the optimum cable size. Briefly, the NPV, or net present value, represents the difference between the present value of savings in the cost of losses over the time period, the 20-year period that we've selected, and the increase in capital expenditure required to purchase a larger cable size. So it tends to offset the money you gain from saving on losses versus the extra cost of paying for a larger cable. It's not a difficult formula, and it's fairly simple to program in Excel. So and the different variables that are in the formula are discussed here. Y is the savings in cost of losses in dollars per year. R is an important figure, is a discount rate. So that's, I've used typically 7%, which is what we could reasonably expect to earn in, say, financial markets if we invested the money that we saved from reduced cost of losses. N is the time period in years, and I've used 20 years for a typical electrical asset. And CC is the increase in the capital expenditure in dollars as a result of using a larger cable. For best results, it should take into account all upfront costs, such as installation costs, but in this example I've only used just the cable cost. I guess if you wanted to really delve deeper into energy efficient cable selection, you would include those other upfront cable costs, which I would expect that major installation contractors would already be looking at doing if they're not already doing so now. So what we've got to do is add the NPV value to the same table, and I've left off a few of the columns for simplicity, and now we find when we add the NPV value that 300 square mil turns out to be the optimum cable size. I mean, I can let people study that for a couple of seconds. Like I said, using spreadsheet tools makes this this very simple. Some observations that I can make out of this: the cable size with the highest NPV does not always align with the previous table, which is where we had seemingly the lowest total cost. And like I was explaining, because of the influence of the interest that you can earn on the savings from the paying for less for the cost of losses, and many cable sizes greater than the minimum size will yield a benefit in terms of loss saving, but eventually there will be a plateau that's reached where increasing the cable size no longer yields a cost benefit, and you might actually get into a situation where you start getting an increase in total cost. So that's where the NPV starts to fall, for example. The larger the cable size selected, the longer will be the payback period. So, for example, one size larger, so the 120 square mil, will pay itself back in 1 year, but for say the 300 square mil, it'll require more than 3 years to pay back. So this is the number of years to pay back the cost of the cost of putting in the larger cable, which we consider the overall estimate for the life of the asset of 20 years. They are still relatively short. Like I said, I've covered some of the observations on the previous slide because that's where they were most relevant. The NPV, optimum cable size, has got the highest NPV. My suggestions are that this economic or energy efficient selection method is not likely to be applied to domestic applications, but is expected to yield greater results or great benefits for commercial properties, say larger housing complexes and industrial sites where energy usage is greater, and therefore so are the benefits. So where do we go from here? Utilising forums such as this to provide ongoing education of the industry to raise awareness of this alternative or enhanced cable selection method. That's one way of increasing the awareness of this topic. And what we're also doing is we're adding a worked example into AS 3008. Previously this had not been touched within that standard, so we're adding an example into that standard. I'm currently involved in that standard, and it is in progress as I speak. The revision of that standard AS 3008 is expected to be published just prior to the end of 2015, so it's not too far away. With regards to how standards work, it's certainly not too far away. If people want to read a little bit further, I mentioned a paper that was published on Voltimum earlier this year that I wrote, and there's some other useful reading if people want to get into the more detailed application of this topic. And I've mentioned a few here. The IEC standard 287-3-2, I've already mentioned it, and there are many parts to this standard, and one part is devoted to this topic. and that's called Part 3, Subsection 2, Economic Optimisation of Power Cable Size. And I thought it was important to note that this is nothing new. This particular standard replaced IEC 1059, which was first published in 1991. So there has been information around on this topic for quite some time, for over 2 decades. So I guess it's been I guess a little slow for industry to take this up and really run with this with these principles. And the other information that might be interesting to read for people is a technical article that has been put out by AusEng on the ICAA website called Principles of Economic and Energy Efficient Cable Sizing. So that's also another interesting article to read. That just about wraps up my presentation. I haven't seen any other questions come in, so I hope this was of great interest to everyone, and I hope everyone got something. Has anyone got any questions? There's nothing coming through. There's no other slides to my presentation. I might just give people a few more moments just to consider whether they have any other questions.
Martin, it's Ian here. There is a question there from somebody saying, why did you square the utilisation?
Excellent. I'm glad someone picked that up, because the utilisation factor has to be applied to the current, and because losses are proportional to I squared R, then I have squared the utilisation factor in that formula. If you applied the utilisation factor before calculating losses, in other words, you applied the 80% to the current before you worked out the losses, then you would just use the 0.8. Did that explain things okay? I see there's another question about getting copies of the slide, and I think, as Ian mentioned, that this will be available on the Voltimum website for review at a later date. There's one other question come in. In three-phase situations, yes, all three conductors are assumed to be carrying the same current. So the utilisation factor, as applied, in the previous question, has to be applied to all three conductors. And I might add, the example that I did is a fairly simplistic one, and what I'm doing is demonstrating the principles. Things can get very much more complicated if you have combinations of single phase and three-phase loads. I haven't considered a neutral current, for example. Another question has come in. And that's sort of further to what I'm just talking about. That's when it becomes more complicated. You need to, whatever the situation is, if you've got a three-phase system, running into an installation, and you've got predominantly single-phase loads, then you need to treat each phase individually and work out the losses associated with each phase current. So, but for three-phase systems, normally they're assumed to be reasonably well balanced. Simon, I'm not sure if I've answered your question properly. Maybe can you just let me know if I've covered what you were looking for? Okay, the question's about a three-phase motor only having one fully loaded conductor, the other two are partially loaded. Well, normally in a three-phase motor there would be a fairly good balance between all three phases, and therefore the phase current would be very, very similar, unless this is a special type of motor that has unbalanced phase currents. Normally, as I said, the phase currents would be reasonably well balanced. But certainly, like regardless of the installation, if you know that you know, one phase or two phases are carrying different currents than the other phase, then yes, they'll have different losses, and the calculations need to be done on a phase by phase basis. My calculations were based on the three-phase systems where the phase currents were balanced.